Good afternoon, all, or good evening. I'm Fuad Rahimov. I'm original from Baku, Azerbaijan. I'll just go over briefly on this topic. So basically, this is about the well integrity application on line and inflow test. I will just skip contents. I will describe throughout the slide. So basically, what's inflow test? Just as a reminder for maybe someone on this call who doesn't come from oil and gas background, this is about performing the test to downhole barriers, and it's performed in the direction of flow. And normally are the final test before the well is handed over from completion from drilling to completion, and then once we assure the integrity of liner, and then we go and proceed and run the hole with the completion. And then we basically flow test, we create under balanced state that allows potential flow, and we test the barriers, and we make sure that we apply the maximum differential pressure. So basically, to make it kind of overview, the oil and gas industry, the well integrity standards do not set hard requirements on how to interpret liner and flow tests. There are some well integrity guidelines that I took from the other various literature, like UK oil and gas, APR RP96, and one book in well control, Crompton's book, Well Control for Completions Intervention book. All these methods, they say that Horner plots may be used to differentiate, but there is no like kind of explanation how to adopt the Horner plot. There's only one book, again, Crompton's book. This is the book that usually all the well control materials refer to. And then in the book, Crompton shows that we can make a plot of flow rate against Horner time x-axis and drawing the straight line, and then comparing if the line intersects with x-axis, and then if it's steamed, the line is tight. If it's crosses y-axis, it's steamed, liner is leaking. There's just only one plot, but however, the Horner technique itself isn't applicable to liner and flow test. I will not go over all of this because it's going to take a while. Just I will mention the most important ones. The number one is probably the data linearization, because during the liner and flow test, what we are doing is assessing if there's flow or a continuous, or the flow is going to cease. Basically, the flow during the liner and flow test is due to thermal expansion. And thermal expansion is heat transfer. Transient heat transfer is not linear. In fact, the heat transfer follows the exponential nature. The equation itself is partial differential equation, but if you solve this partial equation, you will end up with the exponential decay function, which is obviously nonlinear, whereas the Horner technique is based on the data linearization. So basically, it linearizes data on a semi-log scale and trying to make some predictions. The other one about the functional asymptote, I will not go to this. Inherent assumptions. The other assumption is that Horner technique mentions that you have constant temperature, whereas during liner flow test, the temperature is not constant. I mean, the whole point of the whole the flow is from the thermal expansion. So temperature is actually converging to the institute value. So there's no way the temperature is constant. Otherwise, there will not be flow. So this is the most important non-compliances of applying a Horner technique. Again, there is no hard requirement on this. So again, the equation itself, I will not go all these equations, but I will mention only the most important ones. The most important one is that again, if you solve the transient heat equation, you will end up with exponential decay function. So exponential decay function, as shown, is it has negative value, negative alpha lambda square and t. So basically, t is always positive. It's your time. Alpha is always is also positive because it's your coefficient of thermal expansion, and your the lambda is the eigenvalues. So I'll come to this on later slide, but the most important part of the slide is just we have to memorize the temperature is following exponential decay fashion. Okay. So what's eigenvalue anyways? Eigenvalues naturally arise due to Bessel's term. Anyone doesn't come from math background, Bessel's is when you try to solve the heat transfer in cylindrical coordinates, you end up with this Bessel's oscillations, and every eigenvalues that satisfy boundary condition, every number that satisfies boundary condition is an eigenvalue, and the product of eigenvalue with radius must be equal to the nth zero. I mean, this is deep math. I'll only focus on the practical side. I will skip the theory. So basically, if we look at this, the chart in this acceptance criteria. So basically, I just mentioned in the previous slides, the temperature itself, if we solve the partial differential equation, we end up with exponential decay function, and the exponential decay function has negative lambda t. Okay, so t is always positive. It's your time duration. Whereas lambda, if it's positive, the exponent term will be positive because you have negative already. If your lambda is also negative, you end up with the positive exponential decay function, and the positive term will drive your function away. So basically, to put in non-technical terms, so basically what we are trying to assess during linear inflow test, is the flow going to cease or not? I mean, that's the whole point. Usually the test takes around 4 hours minimum, 3-4 hours, and extendable up to 7-8 hours. So during this, from 3 hours to 8 hours, we are trying to see if that exponential decay function is going towards zero, or exponential decay function is just blowing up. In math terms, if the exponential decay function, because you have negative sign, if it's the exponent also negative, then negative will be positive. So then the function will not converge to zero because the term exponent is positive. Whereas if you have lambda positive, then the exponent will stay negative, and it will draw the function to zero, which is exactly what we are after during this linear flow test. On the right side, you see the Bessel's equation. This is the zeroth order Bessel's equation. So basically, the criteria number one, the eigenvalues, which is lambda, should always be positive, because if it's negative, the exponent will be positive. And the other acceptance criteria is that those oscillations you see in the right side of the plot, those oscillations should decrease over time. So basically, the reason why it should decrease is because the multiplication of constants before the function derives the amplitude, derives the height of those oscillations. And with the time, as the temperature converges to the boundary, to the initial temperature value, the oscillations and should follow the descending trend. I'll apply in the next slides. I will show the application. The other point that we can visualize the direction fields. So direction fields in math term, direction fields show the stabilization. Okay, so on the left side you can see convergent case. On the right side you can see divergent case. As mentioned before, for the convergent case, if the lambda is positive, then it will drive your exponent term negative, and the negative exponent term will drive the function zero. That's exactly what we see on the left side. We can see all these little arrows pointing towards zero line. Just as a side note, those lines are actually your derivatives. Okay, if you solve the ordinary differential equation, you end up with those little arrows which show the slopes or derivatives. If the positive, you have reached the stability condition, which in other words mean if you are going towards zero line, then you are in convergent case. The well has reached stability. But for the divergent case, where the lambda negative, again, if your lambda is negative, negative will be positive, so it will draw the function away from zero line. That's exactly what we see on the divergent case. So lambda positive is convergent case, negative divergent case. Field application. So this is pure theory. Okay, this is like if you look at the heat transfer equations or ordinary differential equations, solving all this, we end up with the Bessel's function, right? And then trying to apply this to the field data. I had some challenges. Number one, I had to make sure that the data that I have is reliable. Number one, if the data is not reliable, doesn't make any sense. You cannot verify its applicability, right? So basically, there are some step-by-step process that you can go through to apply this. So number one, exponential decay model. first of all, we have to make sure that the model that we have, the data we have, is following exponential decay model. The reason why, because the function itself, the temperature function itself is following exponential decay function. If the data is not following exponential decay function, all this theory isn't applicable. I mean, you have some other source, your line is leaking. Eigenvalue analysis, this is the lambda. So you have two kinds of eigenvalue analysis, fitted, computed. I will show in the next slides what those are, and then test data segmentation. So usually the linear flow test, in my experience, I've never done linear flow test less than 3 hours, because less than 3 hours, you are still transient state. You have never reached to steady state, right? So that's why you have to segment the data into 3 or 4 portions each 60 minutes and compare those portions and see if you have a convergent case or if you have divergent case, and then evaluation of amplitudes. Remember what I was talking about, the amplitudes of the business oscillations. Those are the amplitudes, the heights. If you follow the real data, those amplitudes should decrease because your temperature should converge to the in-situ value, and then the amplitudes of those oscillations should decrease. So after going through all this, I tried to match the inflow test data from the field on this theory. So I applied more than 10 wells, 10 well data, real field data, and all this data, even if you don't know all this theory, even if you don't, let's say, solve all these heat transfer equations or exponential decay functions, if you just have the raw data from linear flow test, you go to Excel and plot the data, you will have exponential decay function. And that was the very first time when I asked myself, why do all this data follow exponential decay nature? And the reason was obvious, because once you solve the equation, it has exponential decay function. So if the data itself is not following exponential decay model, then the data is not accurate, or you have linear leak. So it is a very first gate to assess if the data is robust or not. So basically, the test in my case, this specific field case, lasted 320 minutes. So you have initial return volume was 9 liters, and this is the repeated value, whereas actual was 9.2. So 9.6, 9.2. So you have very good match. And then I tried to apply some metrics like R square and residual stress error and prox, and those both metrics told me that the data is accurate in terms of the fitting with exponential decay function. So on the right side, you can see all those field data, all those like pool data, and then you have curved line, field curve line, right? So you can see that the lambda itself. Let me show you. You can see the lambda itself in the red box is positive. So lambda is positive, so that means you have exponent term which is negative. So negative positive will stay negative, and that will force your function to reach stability. Okay. Once you try to do the eigenvalues, but not fitted, but in this case, you will go computed eigenvalues. The reason why computed eigenvalues, because again, the functions follow exponential decay. So you can pretty much calculate approximately, you can predict how much fluids you're going to get during the inflow test, right? And then you can compare your computed eigenvalues against your real data. So once you have these computed eigenvalues, you will see a very nice decreasing trend. I mean, this tells the whole story, right? So the early stage, you have decay rates is very, very high. If you look at the decay rates, the very first case, you have 0.025, and then just decreasing, and then somehow reaching a plateau, but not that much, because you still have some noise in the data, some non-boundary conditions. But what's the most important trend line in this plot is that you have this nice descending fashion, and the reason why, because as the test goes on, the temperatures is following the geothermal profile, right? And once you have geothermal profile, once you are close to steady state, theoretically your thermal expansion should be decreased, and that's exactly what we are getting from the plot. And that's exactly what you are seeing, is that by the time as you are converging the steady state, you will see this nicely descending fashion of eigenvalues. And then the other point over the Horner's technique is that again, Horner technique, just as a side note, Horner technique is used primarily in reservoir engineering. It's never meant to use for laminar flow test. Its original purpose is reservoir engineering, and we have nothing to say against it. It's well proven, robust method, and no one is here to challenge how Horner is used for this purpose. But when it comes to application of Horner to the heat transfer, that's where things become messy, because in this equation, look at this T0. If that was in reservoir engineering, you have pretty much exact clear idea what T0 should be. But in thermal expansion, not that much. You have two values, 60 and 240 minutes. And if you look at these plots, you have no way of saying if it's going to cross x-axis or it's going to cross y-axis. If you look at the 60 minutes, T0, 60 minutes, and you don't know if the liner is leaking or liner is holding pressure. So that's why you have to extend the test unnecessarily. And the extended test, I mean, people coming from the field will know this additional error time, and everyone start losing their mind. Why are we extending the test, and so on and so forth. That's why we have to be like 100% accurate when we are sending instructions and when we are applying something, right? So when we are trying to segment this inflow test data into 4 segments, let's say in my case the test lasted 320 minutes, right? So it's around 7 hours. So each each segment I took segment 1 as 8 minutes, and then segment 2 8 minutes. So basically I divided all those segments 8 minutes each and tried to compare how those eigenvalues and C compare. C, as a side note, just forget about this equation. C just means the height, the amplitude of this equation. So basically, after each time, as it can be seen from the plot, all these C's, which is the amplitude of the spatial temperature variation, is following this nicely decreasing trend, whereas the lambda is also following this descending trend. So that both would imply that you are in converging gradually to the steady state from transient state heat transfer. So conclusion, current interpretation, unfortunately, won't take the standards for whether it's API RP96, UK oil and gas. I mean, I think NORSOC D010. So one of the other prominent won't take a standard doesn't also mention any liner flow test acceptance criteria. It just mentions liner has to be in flow test, but there's no acceptance criteria, hard requirements across the industry standard. So that's why they were loosely suggesting this Horner's technique without much guidance. So proposed model just take the vulgar physics and try to solve the transient heat equation, end up with exponential decaying function, and then use math tool, which is the stability tool, eigenvalue linear algebra, and try to apply this to the real world case scenario, and then see if the line is going to stop the pressure, if the thermal expansion is going to cease, or line is going to hold the pressure. And then once you build this nice model, and then you apply to the field, and then see if the model makes sense or not. So basically, this is the my SP paper. You can go and check this paper, use eigenvalue stability analysis for laminar flow test interpretation. I believe that's it, because this 15-20 minutes is very little amount of time to go over all this, but I tried to summarize as much as I could. Any questions?